Dear students, welcome to EPG Pathshala. This module is entitled Statistical Hypothesis Testing and P-Values. As you can see, the statistical hypothesis testing occupies the central role in the statistics. So it's also called significance testing. This is the current gold standard in scientific experimentations and scientific methodology. The scientific methodology has been developed for many years, for the last many centuries, probably from the Bacon, the Francis Bacon's Novum Organum. So Baconian method has culminated into this particular statistical hypothesis testing through many intermediate, and especially the falsification. The scientific theories are open for falsification, a concept by the British philosopher of science Karl Popper. So Popper's falsification and Baconian method has been implemented through this particular excellent strategy to prove a scientific hypothesis. The prior hypothesis is there. Now I have to prove or disprove that particular hypothesis. We have to use a statistical hypothesis testing. This significance testing method has been developed mainly by Fisher. The Ronald Aylmer Fisher. He is basically an American. He was actually a population geneticist, so he is considered to be the father of this particular discipline of statistics. So statistical hypothesis testing or significance testing tests the validity of our scientific hypothesis. So this is extremely important for systematic scientific work, including the experimentation. So now let us see how this particular testing works. So scientific methodology has been developed with the Francis Bacon's Novum Organum, published in 1620. Scientific claims have to be independently verifiable. Falsifiability of the Karl Popper. So the British philosopher of science Karl Popper has said that the scientific claims have to be independently verifiable. So if a claim is, you can never verify a claim. For example, Bacon famously said something called this one, the Russell. The Russell famously said something called teapot, Russell's teapot. There is a lone teapot orbiting the sun between Earth and Mars in the Kuiper belt. So if you make this kind of claim, how will you prove it? If you do not believe that particular teapot exists, then go and disprove it. So in that kind of way, the science will never do that. It's only the pseudoscience will always make this kind of claim. This is called the philosophical burden of proof. So scientific claims have to be verifiable. So that is a hallmark of this particular Popper's falsifiability. So science progresses by repeated falsification of earlier claims. So that is actually a fundamental property attribute of the scientific theories. And now on the other side, according to yet another philosopher of the science, Thomas Kuhn, science progresses through unconventional revolution of the ideas. That is called a paradigm shift. The current gold standard of the scientific methodology for the experimental science is the statistical hypothesis testing. Now let us see an analogy. Are you lucky? Let's find out by a coin toss. So toss the coin 10 times. If you get 6 times or more, you are lucky. So that is my hypothesis, right? Before even doing your coin toss, I say if you get 6 times or more the head, you are lucky. Now you do that coin toss, the result is 6 head and 4 tail. Now you have to conclude you are lucky. So had my earlier conclusion been if you get 5 times or more head you are lucky, then again that is absolutely fine. But had my earlier theory had been 8 times or more head, then the result says it is you are not lucky. So you cannot actually change your threshold value, that is 6 times or to 8 times. That actually tweaking is not possible. So that is how the scientific hypothesis testing work. So statistical hypothesis testing works by the following the steps. The first step is to define the alpha, that is the threshold p-value. I will explain to you what the p-value is subsequently in this module. Define the null hypothesis, that is also called H0. Define the alternate hypothesis HA. Finally calculate p-value and decide the fate of the scientific hypothesis. First of all, I told you define the alpha, that is threshold p-value. alpha, the first we have to define the threshold p-value, that is also called significance level or alpha, before you do the experiment. Ideally, you should set this value based on the relative consequences of falsely finding a significance, that is false positive, or missing a true significance, a false negative. So the significance level alpha is chosen based upon your tolerance for the false positive. The alpha is directly connected to the false positive. I'll explain to you how this connection is happening later. In practice, the threshold value, that is called alpha, is almost always set to 0.05. In the earlier module, I have explained to you it is 95% confidence level is used for the confidence interval. 95% confidence level is equal to 0.05 alpha, so that is the current standard for throughout the statistics. So 0.05 means 5%, or 100 minus 5% is 95% confidence level. If your value is top 2.5% or bottom 2.5%, that is a significant value. So significant score has to be top 2.5% or bottom 2.5%. That means more than 98.5 percentile or less than 2.5 percentile. So that is what your significance score. Suppose the mean is 11 marks and standard deviation is 4 marks. If a student gets 2 marks, the value is considered significant. Why? Because 11 marks subtracted by 2 times the standard deviation 4. So 11 minus 8, which is still higher than this particular score 2 mark. So it is significant. So in this case, significantly low, because the value is lesser than 2 standard deviation about sample mean. P-value for this should be less than 0.05. So whatever mean you do to calculate the p-value, for example student t-test, you can do, the p-value will definitely be lesser than 0.05 for that particular problem. You can simply do that particular rule of thumb approximation for this calculation. Alpha means the probability of incorrectly rejecting the null hypothesis. If the null hypothesis is actually true, so incorrectly rejecting the null hypothesis, that means you have rejected the null hypothesis. Null hypothesis of no effect is being rejected, but that rejection is incorrect. So there is nothing but false positive. Fraction of false positives out of all results where null hypothesis is actually true. So that is what the alpha means. Null hypothesis, what is that? If you are comparing 2 means, the null hypothesis is that the 2 populations have the same mean. Population A mean is equal to population B mean is called the null hypothesis. When analyzing an experiment, the null hypothesis is usually the opposite of the experimental hypothesis. Your experimental or alternate hypothesis is the reason you did that particular experiment, right? So null hypothesis is that the 2 populations have the same mean or the treatment has no effect. That is what the null hypothesis is. Second part is to calculate the p-value. So you can perform any kind of standard test, for example student t-test, to calculate the p-value. If the p-value, example 0.04, is less than the threshold, that is 0.05, state that you reject the null hypothesis and that the difference is statistically significant. But remember, you cannot conclude that this alternate hypothesis is true. If the p-value, that is 0.06, is greater than the threshold, then you state that do not reject the null hypothesis and the difference is not statistically significant. You cannot conclude that the null hypothesis is true. All you can say is that you don't have sufficient evidence to reject the null hypothesis. So that particular argument is known as argument by contradiction or negation, commonly used in logic and philosophy, but not really much in science. Of course, it is also used in jurisdiction in law. An analogy will be a juror pronouncing the verdict guilty or not guilty. The juror or a judge can never say that the accused is innocent. That term is never used here. The conclusion is also very crisp. No one likes uncertainty. She cannot say that I don't know or probably he is guilty. That kind of subjectivity can never be part of this kind of scientific experimentation. And certain notations can also be used. It depends upon the p-value, right? If the p-value is very, very low, like less than 0.0001, extremely significant can be used, and you can use a notation of 4 star to say how significant that particular p-value is. So it depends upon the p-value which you got, right? If your p-value is very low, you can always say it is highly significant. So there is a scope for errors, type 1 error and type 2 error. You have made type 1 error if you wrongly reject the null hypothesis. See, you reject the null hypothesis and you conclude that there is a difference, significant difference, but that rejection is wrong. That is what type 1 error. So in other words, type 1 error is nothing but false positive. Now if you say type 2 error, it is nothing but false negative. But you should know that you will never know, is it an error or not an error? Is it actually genuine significant finding in your test, or is it erroneous type 1 or type 2 error if you work with empirical data set? But if you do the simulation, you will know it, otherwise you will never know it. So as you see in this particular image, you can say that, for one example would be, the reality is the person is, for example, a person is truly HIV negative. Now your report says the positive, the report say it is positive. As you see, the person is truly it is negative, so it is known as false positive. If the test says negative for HIV negative, there is no problem. And if the person is truly HIV positive and test say it is positive, again no problem. But if a person is truly HIV positive and test say that it's negative, then it's called type 2 error or false negative. That is exactly type 1 error and type 2 error is, and I've also said an example of the spam as well as the verdict, the judicial verdict, guilty or not guilty. You can see that is exactly the type 1 error and type 2 error. P-value, what is p-value? If the null hypothesis is true, what is the probability that random sampling would lead to the difference as large or larger than observed in that study? So you should know the p-value definition starts with the word if the null hypothesis is true. So that is our premise. The null hypothesis is true. So premise. Then we do that experiment. Then we will check the validity of that particular premise. So this is basically a deductive approach that we use it in the logic. Right. So given the null hypothesis is true, null hypothesis, as I explained earlier, that means that there is not much significant difference between the two values. So there is no correlation or regression, right? So what is the probability that the random sampling would lead to the difference as large or larger than that observed in this study? That is what the p-value is. So if a study compared means of two groups and got a p-value of 0.03, what does that mean? That means that if two population means are identical, that means null hypothesis is true, there is 3% chance of observing a difference as large or larger than what you observed in that particular study. So as the chance is very low, 0.03 is, 3% is quite low, you conclude that the means are not identical. Another interpretation, random sampling from the identical populations would lead to a difference smaller than you observed in 97% of the experiments and larger than you observed in 3% of the experiment. That is what a p-value says. So as you see, the p-value is not very reproducible. There is a very big problem with the p-value. If you do the same thing, the sampling again and again, the p-value, you are not going to get the exact same p-value. There is a big problem. It's confusing because null hypothesis is almost always false. So there is no point in disproving the null hypothesis, isn't it? So logic works backwards from population to the sample. So it's basically nothing but logical deduction. It's counterintuitive, argument by contradiction. So that is why it is a little bit confusing for most of the people. One-tail p-values are used when predictions are made before the experiment about the direction. So if you know the directionality of your effect, then you use the one-tail p-value. So if the null hypothesis were true, what is the chance that the random sampling would lead to 40% or more reduction in infection rate in those treated with antibiotics than the placebos? So see that I'm saying lead to 40% or more reduction. I know that it will reduce. Why? because it's antibiotic. I'm treating with antibiotic, it will definitely reduce it. Antibiotics, as I know very well, no known antibiotics are going to increase number of bacterial colonies, right? So antibiotics are always detrimental to the bacteria, so it's only a reduction. So I can safely use it is one tail p-value. Another example is fever. Fever is always up, right? So nobody will actually get lower than 37 degrees, that is highly unlikely. So fever, as per the definition, it is more than 36. So if I want to say about fever, it is always positive. So profit, again, profit is always plus, it can never be in minus. So had it been minus, it's not a profit, it's a loss. Does your new antibiotic impairs the kidney function, increase serum creatinine? So null hypothesis would be drug does not increase the serum creatinine. Alternate would be drug does increase serum creatinine. So your null hypothesis, if it contains that particular symbol, is that not equal to or does not increase, then probably you should use the one tail p-value. But remember that when in doubt, always stick with two tail p-values, because one tail p-values are always less than the two tail p-value. So investigators like one tail p-value to prove their hypothesis. As you see, most of us, the investigators, are looking for getting a very, very low p-value to say that the result is extremely significant, right? To get very low p-value is very easy to stick with one tail p-value, but that is erroneous. Nowadays, reviewers criticize any use of one tail p-value, no matter how well the justification be. Now there is another type of error that is called type 3 error, alternatively called type S error. So when the directionality of the effect goes opposite to the direction of the prediction. So that is especially prone if you use one tail p-value. So you predict in one direction, but the effect goes the other direction, then the directionality, entire directionality reverses, then you would have made this type 3 error. One example here, anti-arrhythmia drugs like atenolol to control the atrial and ventricular fibrillation. So arrhythmia is nothing but irregular heartbeat, right? So for this irregular heartbeats, you have to use atrial and ventricular fibrillation. There's some drugs, right? Fibrillation is nothing but contraction, sudden contraction of these auricles and ventricles. So you have to use drugs like atenolol to stop it. So there is a huge study by the name CAST, Cardiac Arrhythmia Suppression Trial. So it concluded that anti-arrhythmia drugs would either prolong the life of the patients or no effect, so that they choose one tail p-value. So the drugs will, like antibiotics, these anti-arrhythmia drugs they theorized would either prolong the life or it would have no effect. They didn't consider there could be another effect. It would drastically decrease their life expectancy. There is yet another effect. They didn't consider that particular effect. So they choose one tail p-value. They got a very high one tail p-value score and concluded that there is no effect. Instead of to say that there are two possibilities, is that one possibility is that they would prolong the life or there is no effect. So they concluded that it's no effect. Actually, the patients given the drugs were 4 times more likely to die than the placebo. So the effect went directly in the opposite side. So that is the type 3 error. So significance level and p-value is connected. Significance level alpha is chosen by the experimenter as part of the experimental design before collecting any data. That is extremely important. Even before collecting the data as part of the experimental methodology, you have to framework the design. It should be part of the experimental design, the significance level. You cannot change this after the data collection, and if you do change, it's a cheating. P-value is computed from the data. You reject the null hypothesis if the p-value is less than the threshold p-value alpha that you set earlier. So that is the difference here. Significance level is set part of your scientific design, experimental design, while p-value is what you get out of your data, right? After you analyze your data, you're gonna get the p-value. There is a very famous statement by the statistician James L. Mills. The statement goes this way: if the fishing expedition catches a boat, the fishermen should throw it back and not claim that they were fishing for the boats. If you're going for a fishing and if you get a boot, then you can never reclaim it. You remodify your prior hypothesis that you came there not for fish but for the boot. That is how the normal practice of this particular most of the statisticians or the investigators. So they choose one significance level and do that experiment. For example, they choose 0.05 and they do that experiment, and then they got a higher value. For example, they got instead of 0.05, they got like 0.3. Then they say that later that what the significance level they chose is not really 0.005 or 0.05, but instead they choose a significance level like 0.5. So what they got is 0.3 is lesser than 0.5. So they falsify. They put a different claim. So that kind of falsification is treated as scientific fabrication of the data as well as the p-hacking. So that is should be avoided. So which alpha to be used? Alpha is level of significance. You can use low alpha like 0.01 to have less chance of making type 1 error or false positive. But beware, chance of making type 2 error, that is false negative, is increased. So what are this type 2 error chance of making type 2? Some examples will be, the consequence will be more type 2 error or false negative. Some example, more spam in your inbox, criminal is set free, the test says negative for HIV positive person, a doped athlete is set free, an effective drug is declared as ineffective and abort the drug development. All these are examples of false negative. So the consequence of getting that kind of false negative will be higher if you use a very low alpha. Now if you use a high alpha like 0.1, what would be the consequence? The relative consequence would be you will have less chance of making type 2 error false negative, but beware, chance of making type 1 error false positive is increased. Some consequences are more type 1 error, that is false positive. Some examples are, good email as spam and deleted, an innocent is punished, the test says positive for HIV negative person, an innocent athlete is declared as doped and banned for life, an ineffective drug is declared as effective and marketed. So it all depends upon the tolerability. For example, it's different case by case. It is context dependent. For example, consider the HIV case, right? The test for the HIV, which is more tolerated for you. For example, the test says negative for an HIV positive person. Is it good? Or test say positive for HIV negative person. That is what you call the false positive or false negative, which is actually better. If the test says positive for a HIV negative person, that is actually better, isn't it? Why? Because if the test says positive, then the person will definitely go for further test or reconfirmation test, right? But if the test says negative for a HIV positive person, then the person would think, okay, there is no problem, it will go on, he will not take any therapeutic intervention, he or she. So that is actually wrong. So it actually depends upon the context. So you cannot make a rule of thumb or the same rule for every context. Now alpha is context dependent. Use low alpha like 0.01 to minimize false positive and is ideal for situations when false negatives are tolerated. For example, criminal jurisdiction. Why? It is better to let many guilty persons go free than to falsely convict one innocent person. So that is a common morality questions everywhere in the world, right? Which is better, to let guilty persons go free or falsely convict an innocent person? So which is actually tolerated? So that is why, right, to let guilty person go free is actually better. So that's why low alpha, that to minimize the false positives are better. Now spam filter is also better. Why? It's better to have spam in inbox rather than automatically deleting a spam and deleting that article acceptance or job selection email. The very, very important email deleting, that is actually disastrous, right? That is a catastrophe. Clinical trials for Me Too drug. It's better to abort effective drug development than marketing an ineffective, useless drug when better alternatives are already available. So if the alternatives are available, then why to actually market this Me Too useless drug, right? Use high alpha like 0.1 to minimize the false negatives and ideal for situations when false positives are tolerated. For example, civil jurisdiction. It's better to punish many innocent than let one huge illegal corporation go free. Clinical trial for novel drug. It's better to market an ineffective, useless drug than aborting the development of an effective drug when no drugs are already available in the market. So that is the context of this significance level. So traditional 2 sigma threshold, that is actually 95% of the confidence level or 0.05 is a 2 sigma threshold, right? 95% of elements will be within 2 standard deviations of the mean. That is the 2 sigma rule or 3 sigma rule or empirical rule. There are so many different ways of saying the same rule. So there is actually something called 2 sigma rule, but in the case of particle physics, it usually go to 3 sigma, that is basically 0.003 for the significance that is commonly used for the evidence of a particle, and 5 sigma threshold, that is actually it's extremely low number, right? For the discovery of a new particle, if you want to affirm that it's a new particle, for example a boson, when the boson paper published, so it needs to cross this 5 sigma threshold. As you see, it's extremely difficult to achieve that particular target unless your research is purely true, right? So that's why it's very, very difficult. Now coming to further things like the level of significance I already explained to you. There is something called statistical power and false discovery rate. I will tell you what it is, right? So as you can see in this slide, when the null hypothesis is true, the decision is to reject the null hypothesis. Again, that's an error. There is something called false positive or type 1 error. I already explained to that. That is a quadrant A. Quadrant B and C are no error. These are significant results, right? Now quadrant D is type 2 error or false negative. When would that be? When the null hypothesis is false, decision is do not reject the null hypothesis. That is also called false negative. That is quadrant number D. Now A divided by A plus B, that is alpha or level of significance. It is fraction of false positives when null hypothesis is true. If the null hypothesis is true, what is the probability of incorrectly rejecting it? That is on the right side, you can see the first cell, that is actually A divided by A plus B. That is called the level of significance. Now it becomes more clearer to you how how the significance is being defined as a fraction of false positive when the null hypothesis is true. Second is C by C plus D is a statistical power. It is a fraction of statistically significant results out of the results where the null hypothesis is false. Other words, probability to obtain the statistically significant result assuming a certain effect size in the population. That is called the statistical power. Now A divided by A plus C is a false discovery rate, FDR. It is a fraction of false positives out of the statistically significant results. If the result is statistically significant, what is the probability that the null hypothesis is true? Now coming to the p-value fallacies. The p-value is the probability of rejecting the null hypothesis. Many of the students think that p-value is a probability of rejecting null hypothesis. Is true, it's false. Okay, all of these things are fallacies. These are all misconceptions about the p-value. A high p-value proves that the null hypothesis is true. That is wrong. 1 minus p is the probability that the results will hold up when the experiment is repeated. Again, that is wrong. 1 minus p is a probability that the alternative hypothesis is true. Again, wrong. The p-value is a probability that the null hypothesis is true. Wrong. P-value is a probability that the result was due to the sampling error. Again, wrong. Then what are the correct interpretation of the p-values? In an experiment of this size, if the populations really have the same mean, see, that is what, if the null hypothesis is true, what is the probability of observing at least as large a difference between the sample means as was in fact observed, or as large as or larger than the effect that you observed in this particular experiment. So let's assume you compared the two means and obtained a p-value of 0.03. The correct conclusion is there is a 3% chance of observing a difference as large as you observed even if the two population means are identical. That exactly is the right way of interpreting the p-value. Now, what is a p-hacking or tweaking? The terms refer to, these are basically scientific misconduct, right? So, some examples: you do different tests, parametric, non-parametric, and then finally you pick one with the lowest p-value. That is wrong. Dynamic sample size and stop when the p-value is lower than the threshold sigma, the alpha, the significance level. That is wrong. Slice and dice the data set to get the lowest p. That is wrong. Cherry picking the data set to get the lowest p. Again, it's wrong. Play with outliers. Remove one or more selectively to get the desired p-value. Again, wrong. All of the above are cheating and constitutes a scientific misconduct. The term stargazing is used to refer overemphasizing the p-values. As I told you, there are a lot of problems with the p-value, and overemphasizing the p-value is not a solution, not an answer to any of these problems. Decisions based on p-values are all depend upon the threshold significance level, which is arbitrary. We set the threshold value as part of the experimental design, which is totally arbitrary. P-values depend on sample size. It is easy to get very low p-values with huge sample size with tiny effect, or tiny samples with huge effect. So do not make p-value as a measure of the effect. So in the case of the second one, tiny sample with huge effect, it's okay. But if it's the low p-value is only because of the high sample size with very low effect, it's absolutely, it makes no sense, because the effect matters in most of the scientific experimentation, right? If the effect size is very large, then the scientific experiment is quite good. So p-value, you cannot use a p-value as a proxy for the effect size. P-value answers the question, is there a significant evidence of a difference? So significant evidence of the difference, it's not that. Is there evidence for a significant difference? No. There is a subtle difference between the two things, right? Significant evidence of the difference. So the difference could be minute, but the evidence is significant. So it's nothing to do with the significant difference. The evidence for the difference is not significant. It might not be significant too. So difference might be tiny or scientifically negligible, yet decision based on p-value could be statistically significant, right? Now there is a connection between p-values and confidence interval, and as I told you earlier also, confidence interval is a better way to express the estimate as a population. It is much better to say in confidence interval than the p-values to say how confident you are on your estimate. So if 95% of the confidence interval does not include the null hypothesis, then the p-value should be less than 0.05. If 95% CI does contain null hypothesis, then the p-value must be more than 0.05. So that is a good way of approximating. If you have only the confidence interval, what would be the p-value? So if it's 99% confidence interval, so the p-value has to be less than 0.01. And if it's 90% of confidence interval, p-value has to be 0.1. So the question is that, does that confidence interval contains a null hypothesis or not? Now consider this particular problem here. Here it is comparing the observed body temperature and is 12 with a hypothetical mean value of 37. On the lower panel you can see that the mean plus or minus the confidence interval, right? 95% of the confidence interval, the lower panel, you can see that this particular range does include my 37 degrees. So 37 degrees is my null hypothesis. So it is not significant. So p-value must be more than 0.05. Why? Because my confidence interval is based upon 95%. So that is why p-value has to be more than 0.05. Had it been 90%, then the p-value has to be, it has to be more than 0.1%. So if had it been 99% CI, p-value has to be more than 0.01, right? So there is the connection between the p-value and the confidence interval. In the next slide you can see that comparing the observed body temperature when you increase the n, see that in the earlier problem n was only 12, in this problem n is 130, so n has drastically increased. So you will get, naturally you will get the CI width is narrower, right, the confidence has increased, right. So in this case you can see that observed mean and 95% CI around that observed mean do not include that 37, that is our null hypothesis. So does two things overlap or not overlap is not a question here. So here it is, there is no overlap, but in our earlier case there is an overlap. It doesn't matter. My point is that 95% CI, does it include that range, include that null hypothesis or not? In this case the null hypothesis 37% is not included in the range defined by the 95% CI. So in this case the difference is significant and p-value should be here in this case it is basically p-value should be less than 0.05. So because in this case 95% CI do not include your null hypothesis. So the rule of thumb is that when the sample size are equal or nearly equal, in the case of standard deviation, if two standard deviations are overlap, no conclusion. If two standard deviations do not overlap, again no conclusion. Why? Because standard deviation is not a measure of the precision of your sample statistic, right. Standard deviation is a measure of the variability of that particular sample. How the sample is actually varying too much, then standard deviation will be very high. If the sample the elements are clustered around your sample mean, then your standard deviation will be very low. So standard deviation has nothing to do with the population estimate as a precision. Now standard error of the mean, it could be of still little bit of use if they overlap. Standard error of the mean, as I told you, standard error of the mean is always very narrow, right, comparing with 95% CI. So even in the case of narrow, if two standard error of the mean do overlap, then p-value should definitely be higher than 0.05. So it is not really significant, right. Now if it does not overlap, then what? No, there is no conclusion at all. If they don't overlap, there is absolutely no conclusion, right. Now in the case of 95% CI, if they overlap, again no conclusion. So overlap, but if they do not overlap, 95% CI do not overlap, you can conclude, it's safe to conclude that the p-value is less than 0.05, assuming no multiple comparison. So multiple comparison is another problem that we will discuss in one of the later modules. So if there is no such multiple comparison problem, then it's safe to say that p-value is less than 0.05 if if they do not overlap, if the two confidence 95% CI ranges, that is basically error bars of a graph, do not overlap. You can always say that the p-value should be less than 0.05. So why 0.05? It's because you are calculating 95% CI, so that is the connection. So in summary, statistical hypothesis testing is a very important core discipline of statistics as well as experimental sciences. In any part of the experimental sciences you use this particular thing. So the core elements of this particular hypothesis testing is that you have to choose a significance level as part of your scientific experimentation, the experimental design. Even before doing the experiment, the significance level or alpha has to be chosen. So it is not possible, it's not permittable, or you can call it as cheating if you change that significance level after you do that experiment, right. So as a rule of thumb, the alpha is always chosen as 0.05. Then you do the statistical test after you generate the data, right. So you perform a test like a student t-test, and if you get a score, a p-value which is less than your chosen significance level, then you can say that you are rejecting the null hypothesis of no effect. So if your value is more than that particular value, if your p-value is higher than your the alpha, that is actually significance level, you do not reject the null hypothesis. you can never say that you are accepting the null hypothesis or you are accepting the alternate hypothesis. That is actually a wrong way to conclude the statistical significance testing. So p-value is actually not very reproducible also. It might not have much utility as well. So advised by most of the statisticians are, instead of overly emphasizing on the p-value, which is what you call it as stargazing, it's always better to put due regards and the importance on the confidence limit and confidence interval rather than on the p-values. Thank you.